Good morning, everyone. Thanks for making it out. As an introduction, Dr. Aidan Crilly. I'm one of the fellows. I'm sure you've met a few of them by now. And I'm going to be talking about differentiable programming in numerical modeling. I realise now that this title is incredibly broad, and I will quickly narrow it down. But it's the numerical modeling that I have done in my research before this point, and differentiable programming has proved a really useful tool in introducing some machine learning and AI to what I do. So here's just an outline of what I'll be talking about in this lecture. So I'll give some context, and the numerical modeling is all going to be about solving differential equations, and doing some optimization with differential equations introduces this thing called the adjoint state problem, which I will go through, and hopefully with that being clear, we can go forward to why we need differentiable programming, and then introducing neural networks into differential equations, and finally an example which hopefully shows how this stuff can be useful in relating to modeling physical reality. So yeah, starting off with the context, my research is in nuclear fusion. So in terrestrial fusion, there's some hydrogen isotopes we want to fuse. We have to get them really quite hot, over 100 million degrees, and being dense also helps. So there's a particular approach I'm looking at called inertial confinement, and I'm showing an animation here which shows how the biggest facility that does inertial confinement works. It's called the National Ignition Facility. It's in the US when it restarts. So it's got the world's most energetic laser. It's about 2 megajoules of energy, which isn't actually that much. It's enough to boil a kettle. But the power is about 500 terawatts, which is over 1,000 times the whole of the UK national grid. So you take that energy and you compress it down into a very, very small space of time. And you use that to heat up. I'll wait for it to restart. We're going to use that to heat up and compress our fuel in a quite elaborate looking process. So let's just wait for this to restart. There's 192 beams coming in, and they go off those final optics there and then go into the target chamber. And right in the middle, we have this gold can, which we initially heat up. So we don't directly heat the fuel, we heat up this gold can. And you can see there, laser sitting on the inside, that heats it up. The gold gets very hot, emits X-rays, and those X-rays are used to shine on, there's this capsule in the middle, and that's where the fuel is inside. So we blow off the outside of that capsule, and it's like a spherical rocket. It like implodes inwards, a bit like a spherical piston. And that heats and compresses, much like a piston in a car, but now in every direction, and that fuel gets really, really hot and goes bang and burns. So over a year ago now, they achieved ignition for the first time, so more energy out than delivered with the laser, and they've repeated that 3 times since that date. And my research, along with many other researchers, is predictive modeling of this, because obviously there's a bunch of different design choices. What do we do with 192 lasers? How do we change our targets to do better? And you need a predictive model to do that, because these experiments are really expensive. They cost about $1 million per go, and you can't do that many in a year. So you rely a lot on predictive modeling to be able to do this. So here's an example of a hydrodynamic simulation predicting what this capsule looks like towards the end there, and you can see there's a lot going on. So what is that a lot going on? So it's a very multi-physics problem. So this is a particular code I work on. Here are all the different bits of physics in it. The list goes on. Here's an example of zooming in on that heating up of the gold can and the capsule in the middle. We have the density, the electron temperature, the radiation temperature, all the different things we need to solve for, and we need to solve all these different physical mechanisms to get there. So, yeah.
Sorry, if you go back to the previous slide, is the goal here to maximize the energy out, like this red circle compared to the yellow circle?
So, sorry, the gold is...
No, the goal, like the objective.
Oh, the goal. Yeah, the objective, yeah. Sorry, I thought we were asking about the goal, because that is weird. The goal is, yes, to get more energy out than in. And yeah, they've been at it for quite a long time, but it's only recently that they've managed to achieve that. just to say that the National English Facility, like the laser, the energy here quoted here is in the actual laser, but to fire the laser costs 100 times more than this in energy. So it's not close to energy production, but it's close to break even in terms of it's now, we didn't know we could do this, and now we know we can do it. So going forward, if you think about energy production, a lot of changes need to happen on the laser end as well as on this end, but this was a proof of principle. So it's not about energy production at this point, it's about achieving the most energy output and how far can we go with that. So it's a complicated physical problem. We've all got all these different bits. We made different approximations in this, and we want to make this model as good as possible so that we can do predictions, change designs, and only do a very small number of very expensive experiments. So quite a lot of those physics phenomena on the previous slide are described by differential equations, and nature and differential equations seem to get on pretty well. I realize this is a bit of a philosophical point, but it is kind of weird. Like there's no, Wigner said it's unreasonably effective how good differential equations are at describing nature. They sort of pop out. So the example I give that maybe shows up to begin with, because he invented calculus, as Newton noted, the moon goes in a circle, and if I throw a rock, it goes in a parabola. Those are both ellipses, and second-order differential equations describe ellipses. Therefore, Newton's second law has to be a second-order differential equation. Seems, that's quite unnatural thinking to do at the time. That's why he was a genius. But differential equations show up a lot of the time, so we want to keep those models. They've been describing reality for a very, very long time. But the question we ask is, our shiny new tool of machine learning and AI, can we augment our differential equations and do even better at describing nature? So that's where all these different techniques are going to come in. All right, so what do these differential equations look like? There's two kinds, ordinary and partial. Apologies if you know this, but this lays the groundwork for what's to come. So ordinary differential equations just depends on one single variable, so how something changes in time. So, Newton, I already gave Newton's second law. That's a ordinary differential equation. And for the most part, that change that we're looking at, that independent variable, is time. So one example from the research from one of those models in that code is how we propagate the laser through a plasma. So the velocity of the ray is just a function of the gradient in the electron density. There's this rate of change of that dv dt, and this is an ordinary differential equation. Here's an example of that happening in all its glory, but the basis of it is just this equation here. So we often have ordinary differential equations, and how do we actually solve these? Because that was a continuum in time, whereas on a computer we can't actually resolve that. So instead we break up time into finite steps and approximate this equation. And there's many, many different ways to do it. The simplest being like this forward Euler. So the value at the next time step is the value at the current time step plus the value of the derivative times by the step. So that sort of makes sense. And then it gets more and more exotic as you go from here. The really, really common one is this one, but it's just like evaluating this a mixture of different time steps and positions, and it's a better estimate of what the value of y is at the next time step. But the point being is we go from a differential equation to these are just algebra. So when we talk about differential equations on computers, we're often solving them we are solving them algebraically. So that makes life a bit easier. Oh, have I got Teams notification? Oh, no. I wondered if it was the talk. I'm guessing the people online they would have piped up if they couldn't hear it. Yeah. The other type we have are partial differential equations, where rather than just one independent variable, we have many. These are the far more flavorful of the differential equations, describe cool physics like hydrodynamics. But so instead of there just being one, there's multiple. Often this is space and time. So hydrodynamics is a classic example. Things can change. You have a change in time in where you evolve in time, and then you also have spatial gradients that change how things behave. So a classic example is you have here two fluids, and there's gravity acting on this one is denser than this one, so it wants to move down and get these little ripples, and then this instability forms. And this is described by these equations here, which you can see are all partial differential equations. So we have two derivatives now, so how do we go putting that on a computer? In fact, what we can do is we can discretize space now and leave time, and that partial differential equation now becomes a system of ODEs. So here is an example of the heat equation that says how heat diffuses. It sort of spreads out depending on how curved the temperature profile is. And if we take this second derivative here, we can change it into being, if we evaluate it at a bunch of discrete spatial locations and evaluate a numerical equivalent to the second derivative, this now becomes a bunch of ODEs. Is that sort of clear how that works? I haven't necessarily said how this finite differencing works, but it's not so important. It's that we've taken this thing which is continuous in space, we're now evaluating at discrete points, so we can no longer get those derivatives in the continuum. So instead, we look at adjacent values either side and use that to evaluate the gradient. So this now becomes, T is like a vector for all the different discrete spatial points, and then we can evaluate a derivative by multiplying that by a matrix that does this differencing. So PDEs look like ODEs, and ODEs look like algebra. So how does this all feed into this idea of, like, we want to design things or we want to change how our differential equations work? Often what we're doing when we're looking at how does this plasma behave, we might call the Ford problem. So we have our differential equations all wrapped up very nicely in just some function h here, but you can imagine it's that code chimera. It's tons and tons of different differential equations, but just stating the problem, we have differential equations and we have initial conditions, and that's all we need to do to solve the Ford problem. We need to know where we're starting, and we need to know how to evolve in time, and that will give us everything we need to know. And this is often how we do the design process. A human thinks, what if we did this tweak to how the laser works or whatever? We can use our Ford model to run it forward in time and evaluate the change at the end. And there are some parameters in here that they might be changing. So the example I gave is laser power versus time. They are changing it, so they're doing this optimization process, but they're doing it as a person with intuition. So is there any way we can do that a bit more algorithmically? And that's this idea of an inverse problem. So not only do we want these equations to be satisfied that are in the Ford problem, but we also want to get some figure of merit as good as possible. So we want to minimize some other functions. So we've now got three whole things we want to do here. We want to do as well as possible on something, so that might be optimizing the yield, which is the whole aim of this nuclear physics thing, but it needs to obey the laws of physics, and there are certain initial conditions. So this is a mathematical statement of the goal that we want to do. So now we've spoken about differential equations and sort of defined terms, so we're all up to speed. Now there's this bit here, which is just optimization. So for the time being, if we ignore that these are these constraints, let's just quickly review how you might optimize some function. So there are a few options. So you could do something gradient-based or gradient-free. Got two examples of gradient-free here. Got downhill simplex, which is sort of like you look at a bunch of different points and then find which one's downhill, and this little triangle sort of rolls downhill as it gets closer and closer to the minimum, or Bayesian optimization, where we use a Gaussian process to interpolate between points and then try and evaluate where the maximum is, including the fact that the Gaussian process gives us uncertainty. I think Bayesian optimization has been talked a bit in the other talks, so I won't go through this. The nice thing about these is that you don't need to evaluate a gradient. So if we think back to our differential equation, our Ford problem, evaluating a gradient is quite difficult because you need to take a gradient of all those differential equations, which is quite complicated. So often we can think that a gradient-free approach might be a good thing to this inverse problem. But these scale terribly with number of parameters. So if you're starting to talk about, what can machine learning and AI do for differential equations, they're going to have, at minimum a few hundreds of parameters, and they're going to start to have, millions of parameters. And doing this downhill simplex or the Bayesian optimization in that height of dimensional space is going to be really, really slow. So that's why gradient-based methods are the backbone of AI. So we have to get gradient-based methods into how we do numerical modeling. So gradient-based methods, it's a really, really simple idea of roll downhill. Here are a bunch of different algorithms which are maybe familiar, but they scale really well to a large number of parameters. So we want to try and get gradient-based methods involved in our inverse problem. But how can we do that when we've got this constraint, or we need to obey the laws of physics and need to get gradients through those things? So yeah, this is the statement of the problem. Like, how do we do this efficiently? You could think of doing the forward problem a number of times, slightly tweaking the design parameters to get a finite difference gradient. This has got the same problem as the gradient-free methods. It's really, really inefficient. It scales really badly with number of parameters, and you're running a full forward calculation every single time you want to evaluate a gradient. So instead of, we want to flip that round. Instead of looking at how a single design change influences the answer, and it will tell us how everything changes on the output, even things we don't care about. Say we want to optimize, we want to get the highest temperature. Doing the single design change predicts how everything changes. So it's a bit inefficient. Instead of doing that single design change, every change, can we flip this round and find a method that tells us how every possible design change influences just one aspect, and that one aspect is the thing we want to optimize? That sounds much more efficient, and it's called adjoint state problem, adjoint method. We'll see what people define as the adjoint, but this is what we want to try and get at. So I've got a very simple example to show how you do this sort of constrained optimization problem. This is a relief map of Slieve Donard, which I've been up a few times. Is Newcastle. There's a great lake with those swans, paddle boat swans that you can go around on. So this is just starting here in Donard Park. You can go up along this path, and the constrained optimization intuitive example in here would be, how do you know you've reached the highest point of the path? Highest point you're going to reach while sticking to the path. So obviously, if you just reach the highest point, you just go straight up, go to the peak, you're at the highest point. But we want to include this constraint, which is you have to stick to the path. It's very, very obvious when you think about it, when you're on the path, if it's going down behind you and going down behind you, if it's going down in front of you and going down behind you, you're at the highest point, locally at least. There's other ways you can say it, which will relate to when we get to the mathematical definition. Your path is now tangent with a contour. We can see that this is the highest point here, and it's where our path is in line with one of the contours. Or alternatively, I'm on the path, I'm going along, and if I point in the direction of steepest ascent, it is 90 degrees to where I'm traveling. So those three things are all the same statement of I've reached the highest point while sticking to the path. So how does this relate to, okay, can we speak about this a bit more mathematically? And then after that, can we include the fact that this GP here, which is very, very nicely a path, is actually, you must respect this differential equation. So what we want to do is combine the target and the constraint. So the target here was our f, how high up we are, and our constraint is sticking to the path. And the method is called Lagrange multipliers. Here's Lagrange here, and this is the Lagrangian, named after him. So you basically just do the target plus some lambda times the constraint. And you will note that the constraint, if you're on it, equals 0. So actually, this Lagrangian, when this is respected, is just equal to the target. So if we optimize this, we will make sure that we get to the best point, or reach the highest point, but while sticking to the path. So it's really, really neat. So rather than having two equations that you're trying to keep in your head, you combine them just into one, you've got this Lagrangian. You introduce an extra term, this lambda, which will turn out, we'll name it the adjoint, so that's where that comes from. But target and constraint are in the same place. Cool. So we want to find the optimum of this function. So if we differentiate it with respect to lambda, we get that we get GP, and when it's at its optimum, this equals 0. This is our constraint is satisfied. So that's why we introduced the lambda. If we differentiate with respect to the parameters that we're allowed to change, we get that the gradient in the target is equal to some scalar times the gradient in the constraint, i.e. at the optimum, the gradients are parallel, which is the same thing I was trying to say with you're standing on the path, the direction of steepest descent is 90 degrees to you. That would be the same as the gradients of your path and your target are parallel. So just to illustrate that a bit better, I've simplified Sleeve Donald even more to the blue contours here are our height, and our path here is these different parabolas, and our particular path where g equals 0 is this black point here. You can see at the optimum, if you draw on the gradients, the gradient in the height is pointing this direction, and the gradient in the path is pointing this. They are parallel, or anti-parallel to each other, but lambda can flip the direction. But the magnitude is different, but they are parallel to one another. So that's our optimum. So that's just restated. It's a very obvious sort of intuitive result of, you can also see that these are, the contour and the path are aligned with one another as well. So this is just a mathematical statement. This is the tool that we're going to use, the Lagrange multiplier. So made it nice and simple. Let's bring back our differential equation. Apologies for a slide of maths and no pictures, but now we don't just have parameters, we also have like these state variables that we're solving for on our differential equation. So it could be the density, the temperature, whatever. It's not, our functions are not just functions of parameters, they also have other things in them. Now we want to, we've got our target, we've got our constraint, our differential equations, but let's just follow the same logic as before. Let's combine them using Lagrange multipliers. We get something like this. And then if we find the optimum of our Lagrangian, we get two equations out. We get this one, which we're going to name the adjoint equation, and we get this one, which, because of the same reason of this is 0, means that the gradient of the Laplacian with respect to the parameters is the same as the gradient of our target with respect to the parameters. This is exactly what we want to know, right? We want to know how do we change, what change to the parameters do we need to make a certain change in our target is equal to this. So the idea is you solve the adjoint equation for lambda, and then you plug the lambda value in here, and then you get the gradients that you want. You've now got quite a few equations to solve, but you've got access to the gradients of your target with respect to your parameters, exactly what you wanted. So this is the adjoint state method and how you can include your differential equation, your constraint in your optimization process. So this is why we want differentiable programming. This is why we want, when we solve our differential equations and we've done this discretization and these horrendously complex things, we also at the same time want to solve the adjoint equation to get the gradients that we need. So we will see that if we can solve the forward problem and then backpropagate the gradients through our solution to our differential equation, that will implicitly solve those adjoint equations that we've just showed. So the machine learning idea of backpropagation is exactly the same as solving these adjoint equations. So what we need is a way to do backpropagation through the solution to a differential equation. So that is the big question. How do we get those gradients? And let's start on that journey. So I imagine automatic differentiation is old hat to you guys, but it will quickly blow up with how complicated the graphs look with all the differential equations in. So I thought I would start very simple. So finite difference methods are going to be no good for getting our adjoint equations because of the error term they've got, which is quite large. So in finite difference, we take our gradient, we approximate it as this thing here where we take some finite step. In the limit this went to 0, this would be the true derivative, but instead we keep it as some finite step. The problem is then we accumulate some error proportional to the size of the step or some power of the size of the step. So if you need to solve your differential equation a million times forward in time to get to your endpoint, that error is going to accumulate very, very quickly. So you need something that's much more accurate. So automatic differentiation is something that can give you the analytic derivatives. So it's only wrong to machine precision as opposed to this step size precision. So very, very simple example to sort of go through how it works and which form of automatic differentiation we want to use. So a computer program is a bunch of mathematical functions all done in a certain order. As I said at the beginning, when we're doing differential equations, we make them into algebra. So again, it just boils down to these primitive functions. There's never anything too complicated in there. It's just a lot of functions applied. In this case, let's look at this really simple example of just some sines, exponentials, multiplications together. What does the computational graph for this look like? So we have our x, y, z's, we apply our different functions, and then we get out the answer at the other end. So we've got many different stages in between, but it just computes this thing in steps. Now, we could start from the beginning and look at the gradient with respect to each term here as we take a step forward. This is what's known as forward mode automatic differentiation. And at each step, we look at, okay, my gradient of alpha 4 just depends on the gradient of alpha 1 times alpha 4 because of the exponential. Similarly, for the sine, you get the cosine alpha 3, but the gradient of alpha 3, etc. And this accumulates the gradients as you go forward. The problem is, if you have lots and lots of parameters here, you have to evaluate these gradients each time because I need to set alpha 1 prime to 1 for if I want the x derivative and all the other starting gradients to 0 in order to get the derivative of f with respect to x. So you need to sort of evaluate this gradient for each one of your input parameters and go through the graph another time. So if you have tons and tons of input parameters, which we will often in a machine learning context, and only one thing coming out the other end, then this is quite a bad approach because it takes n number of passes through the graph to get the gradients that you want. And in fact, all optimization processes are many to one because you always optimize some like scalar thing. So it's like a number that represents how well you're doing. So we're always many to one. So if there was a way that we could only do one pass through the computational graph, that would be great, and it would scale really well with a number of parameters. And there is indeed a way, and it's rather than going forward and accumulating gradients, we go backwards and accumulate the gradients. And that starts from one output and accumulates gradients that way. Again, we call something the adjoint. It is very similar to the adjoint from the adjoint state problem. I think the word adjoint gets used too much. But in this case, the adjoint here with the bar is the gradient with respect to the output. And that's what we're going to accumulate coming through the other way. So just to quickly show how that works, let's obscure in some mist the whole complicated rest of this graph, but just start from this bit here. The adjoint of the last term here is just 1 because these are equal to each other. Now, if we take one step back, we've got alpha, the adjoint of alpha 7. We can use the chain rule to split that up into the adjoint of alpha 8 and then this gradient with respect to one another. And then we know from the functional relationship of these two what this thing is. So it is in fact 1 because it's just the sum of these two values. So then we just get 1. Point being, at each step you do the chain rule to go backwards and you use a adjoint value from the previous layer up and you just keep on going back until you will always hit 1 because the output is always a scalar which is equal to the function that you're evaluating. So you start with a 1 at this end and you accumulate the gradients as you go back the other way. So if I reveal the rest, I mean, that's just the chain rule applied. But it's really nice that if you just go one back propagation, you get all the gradients. What we're going to do is build a spider's web here of including that back propagation as a whole separate computational graph that's attached to the first one. And we'll see why we want to do this. So some of the values in the evaluation of the function are actually used to evaluate the gradients. So you can see here, the blue ones is evaluating the function, but some of them are used when we evaluate the gradients. So for example, when you evaluate the gradient with an exponential in there, obviously the exponential appears. So we want to keep hold of that value of alpha 4 because it's useful. So by extending the computational graph, we can work out which values we need to save and which values we can discard. So once we've calculated alpha 7 and calculated alpha 8, we never need this again, so we can get rid of it. So there's some memory efficiency that we can do here. But we know that we need to keep certain values in order to evaluate the gradient. Anyway, point being, we can make our back propagation into a separate computational graph, which is attached to the first one. And I think that was just, cleared what values you need to save, and this single graph allows you to get the forward and the adjoint. Nice. So what is differentiable programming? So now we've introduced automatic differentiation. It seems differential programming is just another word for the same thing. But I want to show where it comes from with a quote here from Jan, who is a big fan of differentiable programming, as you can see. But where this comes from is the fact that now, rather than just having very simple feed-forward, like neural networks being a typical machine learning model, people are starting to put more and more stuff into their machine learning model, like loops and conditionals, and that requires that your automatic differentiation can handle those. Because if it's just a simple feed-forward, then everything's analytic. There's no conditionals would mean you have to split the computational graph, and you have to be able to handle that. So differentiable programming, one way of putting it is that it can handle all those contingencies that you will see in a real program. And what's really nice about it is that by making it very agnostic to what the program is doing, you can now get the derivative of any program, even one that's not a neural network at all, even if one is one that calculates the answer to a differential equation. So if we write our differential equation solver in something which is a differentiable programming framework, we can do automatic differentiation on it and get the gradients. So it's made life a lot easier. So that's what I mean by that. There's a bunch of different frameworks. I'll just give some examples here. I didn't know about this autodiff.org, but they've got all the different libraries for different languages. Unfortunately, the Chimera program that I showed at the beginning is written in Fortran, and the available libraries for automatic differentiation in Fortran are minimal. So a lot of this stuff has to be done in Python, and then you find a way to import that model into your legacy code, shall I put it. Point being, there's broad support in the big names, but if you use some other language, there might be something. Just a simple example of how easy it is in JAX, which is mainly what I use from our simple example. I mean, they've made the barrier to entry incredibly small. I have some function, I want the gradient of it, I just call grad on it and say which argument. That function could be as simple as this, or it could be as complicated as solving the heat equation, but you can still get the gradient. Okay, so a more advanced example to show sort of the power of this. Say we want to compute some integral of some function f of x, which depends on some parameters theta and between two limits. This, if you can't do the analytic derivative, you're probably going to do it with something like adaptive quadrature, by which I mean you sort of take the space between a and b and split it up into rectangles, evaluate the value of the integral, and keep on going until it's converged. That's the adaptive quadrature. So it's a thing that's got loops in, it's got conditionals. So this adaptive quadrature isn't a straightforward program, but we want to be able to differentiate through it. So these are the derivatives that we want to know. Important fact is that this one here, the derivative with respect to theta, we can take it inside the integral sign. So with that, that means that we can now write a program that does follows Leibniz integration rule, for example. So we've got something that computes the adaptive integral. We want to get the gradients from it. We can get the gradient with respect to a and b very easily because these are just minus summation a minus summation b. The complicated one is this one. We need to get the gradient of our f, no matter what it is. So we can use the Jack's grad to get that. And then we want to do adaptive quadrature on that gradient function. So then we do the quadrature on that gradient function. So they're not exactly equal to one another because this might use a different set of rectangles to this one, but if they're properly converged, then this will indeed be the gradient of this integral with respect to theta. So it's really, really powerful and very, very straightforward to build up the complexity of your program and compute derivatives. I'm going to go back to differential equations now, but is there any questions on that stuff?
So
yeah.
Automatic differentiation
yeah.
and differential programming kind of refer to the same thing?
Yeah, so I mean, so this, I would say, in this case, this is exactly the same as automatic differentiation. What we've done here is something slightly different. So rather than just taking this thing here, this has its own computational graph, and then backpropagating gradients through that exact graph. That would be automatic differentiation. This one will do a completely different adaptive quadrature to this one.
Yeah.
So it's not using the computational graph that was built for this. It is we're doing automatic differentiation on the f function here, but then we're doing a completely separate adaptive integral. So that's where I would like sort of draw the line. So this means that this thing here is not the exact gradient of this, because they will use the integrals will be computed differently with different rectangles, whatever. But it is a close approximation to that, and it means that rather than trying to do the automatic differentiation through the adaptive quadrature algorithm, which has got all its ifs and whiles and whatever, it is you just take the gradient inside it and then just compute it as a forward pass of the quadrature. So this is very different to automatic differentiation. Yeah. Cool, back to differential equations. So rather than our function being something super simple, like those sines, exponentials, whatever, what if it's the solution to an ODE? And turns out that's just another graph. I feel like I'm going to be saying that for the rest of this talk. Everything's always a graph. So we've got this thing, differential equation here, which describes exponential decay. It could be the decay of like radioisotopes or something. And a way to solve this is this Euler method here. So we split up time into little steps dt, and then we step forward in time by just repeatedly multiplying our previous number of radioactive isotopes by this thing here. And you can see this is less than 1, so they decay slowly over time. And so then we combine our initial condition, y0, our decay rate, tau, the time step we take, and then we just multiply these together, and that gives us a graph that computes the solution to this ODE. So they often sort of look like this. Your next y value just depends on your previous y value, and then that's combined with the parameters at every single step. So our ODEs often have this sort of graph form. And then we could attach onto the final number of remaining decaying nuclei, and we could compute some function of that, maybe just the number of them, and then we can find how that changes with the different input parameters. So we can just do this and then just do straight automatic differentiation through it. But how does this relate to the maths we talked about, the constrained optimization and the adjoint state problem? So so we've got this, we've got f that is the thing we want to optimize, which is some function. I'm going to put L because we're going to start talking about loss terms. A loss term applied to y at the final value. So what are the adjoint equations that we're actually solving to get the sensitivity of f to the input parameters? They're going to be differential equations themselves. So in order to solve the inverse problem for our differential equation, we're going to have 3 differential equations. So you have to really like differential equations to do this subject. So you've got this one, which describes the forward process. We've got the adjoint process, which tells us how our Lagrange multiplier, our thing that keeps us on the path when we're optimizing, and the parameter gradients, so how f depends on our parameters. So what they look like is this. It stems from that maths with the Lagrangian. I don't think it's too enlightening to go into exactly how you derive it. There's this paper here that shows where, but there's lots of literature about it. But point being is we have our adjoint process and our parameter gradients, and this parameter gradients depends on the adjoint, this which the value here which tells us about the Lagrange multiplier. But interestingly, we also solve these backwards in time, which is quite interesting. So the starting value for alpha here is the gradient of the loss with respect to the terminal value of y. And then our parameter gradients start off equaling 0. And then we solve back from t equals big T back to t equals 0. So we solve this one forward in time and these ones backwards in time. So now you can see why we call it an inverse problem as well. So we've got the formal solution, so we can compare it to what happens when you do automatic differentiation. If we solve these guys backwards in time, then we can get the derivative of f with respect to the decay rate as this thing here. So we know exactly what we should get for the sensitivity of f on the decay rate. So let's check that if we do automatic differentiation on our ODE, that we do get that answer. So yn is just this like little incremental decay times yn minus 1. So if we want to do back propagation a single step, then we do the gradient with respect to tau. We just plug this thing in there. So we're doing one back propagation gradient. If we expand what yn is, then we then get a derivative of yn minus 1 with respect to t, and we know that will depend on yn minus 2. So this thing is just going to keep on exploding back and back propagate through the whole system. So then once we do that, this is what we get as what would be calculated with back propagation. And we can see it's not exactly this, but it's a very, very close approximation to this. So everything out the front is the same. It's just that we've got this 1 minus big T over n tau to the n minus 1, which in the limit that n, which is the number of steps we take, goes to infinity, is the same as the exponential, but it is different. So what we've got here is a numerical approximation to the adjoint. So if you're happy enough with this, then you can just do back propagation, and you've got a solution that way. But you could think about separately solving the adjoint equations. This approach here, where we just leave it as we compute the computational graph for the forward problem, then back propagate, is called discretize, then optimize, which is quite nice to say. There's optimize, then discretize, which is where we keep all these equations as differential equations, solve them all separately, and discretize them separately so they can have their own different time steps. They don't have to be solved on the same time step. And they each have their advantages. We'll see when it comes to neural differential equations and physics-informed neural networks. They have different approaches as well. But this is one approach. If we expand out our computational graph, we're starting to get real spider's web territory here. But we're solving, you can think of it as we're solving 3 ODEs with a shared time step. And the automatic differentiation is just built in that adjoint solution for us for free. So we've got our adjoint process, our parameter gradients. They all talk to each other. We know exactly which values we need to save, so it can be memory efficient. And yeah, so the extending the computational graph shows us that it's 3 separate ODEs that we're solving. They have the same structure. How am I doing for time, by the way? Oh, not too bad. Okay, so just to, rather than having that spider's web showing up every time we want to talk about this, this is sort of the abstraction of it. We have initial conditions, we have parameters, we have the gradients we want to know. We need to compute this first, the forward problem, and then, because we need to compute the forward problem in order to get the value of the loss function, we then get gradients of that and then solve backwards in time. So this whole process is sort of this cycle that goes round and round. Some of the y values in here are needed to solve this. As you can see here, a y value shows up here. So you need to store some of these values or have some way to interpolate these values. Any abstraction that you build like this needs to be able to pass values from the forward to the adjoint. But this is sort of the structure we need. And luckily, people who are good at sort of designing software and writing this have written libraries in order to do this. That allows you to do differentiable programming with ODEs. The one I use is Diffrax, which is on Python JAX, but there's one for Julia, and I'm sure there are others that allow you to do this within this sort of abstraction here. No matter how complicated your differential equation is and how you want to solve the forward problem, it can handle those as far as I'm aware. All right, what if instead of an ODE, it's a PDE? And so I mentioned before those method of lines, you can discretize space, it turns into a bunch of ODEs. So no surprise, it doesn't look too much more complicated. It's now, rather than just a single y value, it's like a vector of y values, and the discretization is like some matrix multiplication that does, say, the second derivative or whatever. So now our PDE solution looks something like this. We have some y value, we use it to compute the spatial gradients, and then we use that to update in time. So we sort of zigzag like this, and the model parameters go like that. But same thing, we can do exactly the same sort of automatic differentiation to get any gradients of model parameters you want to do. So just as a cool example of that, let's backpropagate through a fluid simulation. So let's have it that we've got like a smoke that's inside some fluid that can be moved around by flow in the fluid. And we want to start off from a ring, and we want it to collapse down to give the logo of the place you work, right? So what we want to do is modify the initial conditions, which are those velocities, and get it to match some image after a set amount of time has passed. So now, before you'd have to go, okay, how do you do the adjoint solution to Navier-Stokes? That's quite hard. Now what you do is you write your fluid simulator in a differentiable programming framework. The example I show here is from AutoGrad, if you wanted to try it out and get your own logo made. But anything that can do that differentiation, start off with some densities and some velocities. You have to say that there's some loss function, so some distance between your final image and what you've got after you've run your simulation, and then compute this Jacobian or parameter gradients, whatever you want to call it, and use that to update the initial velocities. It's quite a few parameters, so you need to update the velocities in x and y for every single point on this grid that you've used to solve the fluid equations. But the beauty of this is that you get that all in one backpropagation. You're not just looking at, if I tweak this one parameter, I tweak the velocity in this one cell, what does it do? That would be like the very, very naive forward pass way of doing it. This gets you the Jacobian in one go. I did slightly cheat here. So at some point, I had to stop it and then restart from that point. You can see like all the velocities suddenly flip a little bit, because it wasn't quite, they were all sort of, the sifts sort of disintegrated after a certain amount of time. So at this point here, you can see it all twists a bit. So I cheated a little bit, but I still think it works quite well. So yeah, I mean, once I tried that, I was like, this is really cool. I'm sure there is tons of ways we can improve our physics models using something like this. At which point I thought we might have a quick break because we're going to switch gears a bit. I'm at least going to grab a coffee. So let's say, how long have we got? 5 minutes. It's 11. Carry on. Right. So in the second half, I'm going to be talking more about how we can get more or modern machine learning and AI stuff into differential equations. So the first thing I'm going to start with is, the poster child for machine learning is neural networks. So can we shove a neural network into a differential equation, and what does it give us? So if you're interested in this, Patrick Kidger who wrote Diffrax and all these other libraries supporting this. His thesis is excellent for describing this, so I would recommend it. This is where I learned a lot of the stuff about this, and references in there. But let's say, okay, we've got some dynamical system we want to describe, but there are some effects, some phenomena, we don't really know how to describe them mathematically. So we have how it evolves in time. We've got some known operations, but let's put in something that can describe any term. So a universal function approximator, so our neural network. So now we have our known evolution, and we want to improve it, augment it to describe the terms that we don't know about. And let's do that with a neural network. So this is going to look again exactly like our adjoint state method, but now the parameters are the trainable parameters of the neural network. This, in fact, looks really, really like recurrent neural networks. So in a recurrent neural network, you update the hidden state every step using the neural network, and you just keep track of this. But this looks exactly like forward Euler integration that I showed right at the beginning. We've got our hidden state at time t plus 1 plus that, plus the update function. So you could think of neural differential equations as sort of a continuous time version of recurrent neural networks. So things that recurrent neural networks are good at, neural differential equations may be an improvement on. So one nice thing is, here's a sample from this paper, Chen et al., which sort of shows one of the advantages here. In a recurrent neural network, as you go through, you just discretely step forward one depth at a time, and you update your hidden state. Whereas because differential equations are in continuous time, you don't have to take a fixed time step. You can adapt your time step based on the value of the function. Like if it's very rapidly changing, you should take many small time steps to make sure you get that trajectory right. So instead, an ODE network looks more like this, where you don't just evaluate at one single depth. It's a continuum instead. So you get much smoother trajectories through the hidden output space, or whatever you want to call it. This is sort of a nice relationship between current stuff and what neural differential equations look like. So here are like the advantages. So I spoke about this discretize versus optimize, optimize versus discretize. And the second of which, optimize then discretize, is that you solve the adjoint equations separately. You don't just do back propagation on the forward model. And that can be really memory efficient because you don't need to store any of the forward propagation values. You don't need to know those. But no, you do need to know some of them, but you don't need to store it at every single time step. And you can take adaptive time steps when you're solving the adjoint equations. So it might be that the sensitivity is very low, and you don't need to take the same time steps that you use to evaluate the forward problem, so you can be efficient that way. I've mentioned adaptive quite a lot, but adaptive computation, so there is, I don't know how old, it must be maybe centuries old. I don't know how old Runge-Kutta and all that they are, but it goes back to Euler, so at least it's pretty old. That the solution to ODE is often use adaptive stepping. So if there is a rapid rate of change, you take a small time step to make sure you don't accumulate any error. So now we can do this adaptive computation so that we know what step size we need to take, minimize numerical error, and that's really, really nice. It A, is efficient, but B, makes sure that you get this benefit of it being continuous in time, or approximated continuous in time. This is like quite a nuanced point, but maybe if you're familiar with convolutional neural networks, you can sort of say it's an equivalent to that where convolutional neural networks are local in space, so you don't need many parameters to describe what's going on because your filter is only a certain size, it doesn't encompass the whole image, so you're efficient on parameters. You can think of the time dependence in the neural network being a local nature for time. You don't evaluate all time steps and shove that into a neural network. You only use the local time. So you're only using the local nature in time, so that's parameter efficient again. So I'd say similar to convolutional neural networks, you gain some parameter efficiency by doing this. And obviously, if you've got time series as your data that you're solving for, you want something that can handle time series, and maybe your data doesn't come through on a nice uniform grid, so your current neural network doesn't work. It may be like, you only get some results in close succession, and then it spreads out a bit. You can naturally incorporate this if your data doesn't arrive at uniform times in a neural differential equation. So it's got quite a few benefits. All right, so let's look at a really simple example to show sort of how it works, what it does, what you could think of using it for. And in this one, you can see the physics coming through. Let's learn a circuit model. So you've got a black box which does something with electricity, and you can plug in a voltage source to it, and you can see what current it allows to pass through it. And if you apply a time-varying voltage, you'll get some current response out the other end. But you don't know what components it have in it. It could have a resistor, which sort of restricts how much current you can pass for a given voltage, a capacitor, which sort of stores up charge, or an inductor, which acts a little bit like inertia, like mass. So like you can't change the current too quickly if you've got an inductor in there. So it can have any mix of these, and you have no idea. But you want to have something, a circuit model that says, if I apply this voltage, I'll get this current out. So this is a good example of the neural network. A neural network would be useful. We know it's going to obey some differential equation. We just don't know what the terms are because we've got no idea what's inside the black box. So let's make a neural network predict what the circuit's response to a current is. So here we applied some incoming time-varying voltage, and we get this current response in the blue, and then we train our neural network to match the current as closely as possible. You can see this is over various training epochs. You can see it settles down and gets pretty close. And we only give it we minimize the least square error on the current here. We don't tell it about the rate of change of current, but you can see it still predicts it. We just don't include it in the loss. And you can see it still does a pretty good job. So it's not just like, all right, I can match this shape of function here, and then everything else is gibberish. It is learning some piece of physical information. And we can see that's true because we've trained it on one time-varying voltage. So this is a data set of one. If we change what the time-varying voltage is, it doesn't do too badly, actually. So here in the blue is the real signal. It's never seen before. We apply a new time-varying voltage, and it predicts the current to look like this, and it's pretty close. So for a single time series, it's learned an okay circuit model. I mean, this is the circuit. It's very, very simple and linear, but still, with one training example, it's very efficient on parameters, and it gives something that's a reasonable approximation to the physical reality. So, they're pretty powerful stuff. You can imagine them plugging into much more complicated models, but I thought this might be a nice toy example.
Yeah.
Yeah.
On the right,
Yes.
on the right, is that dl by dt, or is it
di by dt.
Okay.
Yeah. So so just on this point, so the input parameters of the neural network are the current and the derivative of the current. So we know these are useful for modeling a circuit. So we've designed our neural network to take in sensible values, and it predicts the voltage response to these two. But we don't include this didt in the loss, so it's unseen as far as what the real answer is. But it is, we have biased it by choosing the right parameters it should use as an input. So It would perform way worse if your neural network just took the current and tried to predict the rate of change of the current, because we know that the ODEs that relate these two are the I dot appears in the differential equation for the current. So it's useful to have that included in the model. So when you're designing these things, it's not just blind. You need to use what intuition you have about the dynamical system to design a neural network, but that gives it good performance and yeah, works well.
Do you guess back the RLNC kind of constants?
Yeah, you can, yeah.
So is like the neural network would be able to predict those, or is it just
It doesn't know, well, what you would do to pull those out is, I think you would have to like scan over the resonance and then pull out what, and find equivalent RLC circuit for it. But this could, it doesn't need to be just a series connection of RLC. It could be like your actual circuit could have a bunch of parallel branches with different things in. So there isn't one value of. You could use the neural network to give you the total inductance, total impedance of the circuit. That you could do. You couldn't break it down into different resistors and inductors and stuff. Yeah. So you can get that. You can get a model for the total impedance.
I maybe asking because it's similar to like a method that you would use for analyzing like a device.
Yeah.
But you want to get those RLNC.
Yeah.
You want to get like a proper circuit.
Yes.
Like an equivalent circuit out
yeah.
of it.
Yeah, so this doesn't give you an equivalent circuit. It just gives you a total model for the impedance. So it relates current and voltage. So all it needs is the impedance. But you'd have to have a separate model that says, okay, given this impedance, what is a feasible circuit? So it doesn't do that. Yeah. Yeah, I think the normal way of doing a circuit model is like trialing different connections of these, whereas this is just a black box. Okay, so that's neural differential equations. A slightly related, but different in the fact that we sort of, to some extent, don't solve the differential equation when we're doing it, are these physics-informed neural networks. So what they do is, rather than having a differential equation where the neural network represents some of the terms in the differential equation, is we have a neural network that just represents the solution to a differential equation. So it's slightly different. So how do we enforce that our neural network both matches data, but also respects some physical law? So we want to put the physical law into the loss function. And this is how we do it, and this is what's meant by physics-informed. So we have some neural network that is a function of space and time, and it's going to be as close as a predictor as possible to some data y, which is also a function of space and time. But we want it so that we know that our data, our solution, obeys some PDE or ODE, whatever, which has got time derivatives, spatial derivatives in it, whatever. So we know this is true, but we want to have a neural network that just gives us the solution without having to solve a differential equation. So we want to train this to match while respecting this. So what we do is we just add it in as a loss, which seems weird because that means that our loss term is a differential equation. But that's fine because our neural network is a function, has inputs x and t, so we can take any derivatives we want of the neural network and get the time derivative of the neural network, or the second spatial derivative of the neural network. So actually, encoding a PDE is quite easy for a neural network. So let's have an example. Let's have diffusion. So this is just the statement, we want a neural network that represents y, but this is our differential equation. So it involves a time derivative, it involves a spatial derivative. So this is what our loss is going to be. It's going to be usual mean squared error, match our data as well as possible, but we add on an extra term here, which involves derivatives of the neural network. but it is our physical law. So here's an example of training it, of the pin. We have the truth, which is shown as the color map, and then we just select random points within it and record the data from those, and then use that data to train the neural network. If you just gave it the data and said, give me a neural network that matches this data as close as possible, it probably wouldn't have a nice smooth profile. It would just jump all over the place. But what we're saying is the result has to be smooth enough. It has to respect diffusion. So when it does that, you can see that it looks much more similar to the underlying truth, which is the smooth diffusing solution here. So by encoding our law in the loss term, we make our solution look like a solution to the PDE. I will note that it's only approximate, right? Because you could trade, I want to match my data for I want to make sure I obey this equation. Like, this doesn't have to be exactly 0. In fact, it won't be. So, a loss doesn't hard enforce a physical law. It sort of like softly says, you can't stray too far away from looking like diffusion. So that's a bit of an issue with physics-informed neural networks. But the nice thing is it's once it's trained, then you can just ask for any x and t point, and it will very, very quickly compute that without having to need to solve the differential equation. And diffusion is notoriously fickle. If you do a naive sort of finite differencing of this and take a certain time step, it's unstable, and you just get these massive oscillations. So this neural network can very swiftly bypass those. Yeah.
When you have like a parameter here,
Yeah.
you trade off the loss between like the mean squared and the solution to the PDE.
Yeah. So yeah, you can put in a term here, a hyperparameter, that says I really want this to be. This is the more important of the loss terms. Yeah. But it's always the case that this will never actually be 0. So if you really care that your physical law is respected, either you need an absolutely massive term outside this loss term, or you don't want to use a physics-informed neural network. You want to do a neural differential equation. So an example of it doing something slightly more complicated, and also in that optimization process, not only can you train a neural network to predict the solution, if there's unknown terms in your PDE, you can also optimize those to match the data. So it's not just a case of I'll train a neural network to solve an equation. It can be I can train a neural network and some other free parameters to solve an equation. So another example of Navier-Stokes, got quite a lot of Navier-Stokes in this equation, this lecture, sorry. It's like flow past an obstacle. You get these sort of vortical structures behind, like turbulence. And what they did was trained a neural network just looking at this section here, a physics-informed neural network to predict the solution to Navier-Stokes. And they had some unknown parameters outside some of the terms. So this is the correct PDE, this is the Navier-Stokes equations they were solving. And in front of some of the terms, they said, we don't quite know what the values of these parameters are. So the viscosity is this one, and don't know what you call that one. Anyway, so there's a free parameter here, train a neural network that best matches the data, but also these parameters. So if you give it the data exactly, clean data exactly from the solution to Navier-Stokes, it gets really, really close with these trainable parameters, and it does a very good job at actually predicting the pressure or whatever bit of Navier-Stokes you're interested in. If you add a bit of noise, it still does well. So this is really cool, because that means now, rather than having a numerical solution and you're training a neural network to emulate this numerical solution, why bother? Because you could just solve it with a numerical solution. It has noise in now, so you could start using experimental data. You put experimental data in, and you train the neural network to learn, okay, what was the viscosity? And that is a sort of new paradigm, being able to train a PDE on experimental data, and it including noise. Very cool. Okay, so for the last, have we got? Last 30 minutes or so, I'm going to talk about how I've applied these ideas in my research. And a big place for unknowns in physical models comes from this thing known as the closure problem. So often we have large macroscopic scale things we want to describe, the flow of fluids, whatever. That happens on millimeter scales and nanoseconds, whatever. But the point being is that we don't want to have to track the behavior of every single electron and every single nuclei, because we know the physics that describes those, but it becomes incredibly intractable to solve, say, Schrodinger's equation for a mole of electrons. I mean, literally impossible. So you have to make an approximation to go from this microscopic scale description, which we know is very accurate, to a macroscopic scale description, which describes many moles and so many particles that it starts to behave like a continuum. But in doing that, we have to close the equations because the behavior will depend on some of this microscopic physics. We've just swept it under the rug with terms that appear in these equations called closures. So a classic example of this is for describing fluids, we have this thing called the pressure. And if the pressure comes from the microscopic motion of these particles bouncing off surfaces and imparting a force. But then when you start describing it as a fluid, you don't say there are any particles. It's just sort of a continuum. So where does pressure emerge from? Pressure is a microscopic behavior that we need to plug back into our equations in order to solve them. So pressure is like a canonical closure, call it equation state or whatever, but we don't solve for pressure in our equations. We include some model for pressure. So there's so many examples of this, but what we want to do is can we learn better closures so that our macroscopic models capture the microscopic physics better? That's the sort of statement of it. And a big issue with going from the microscopic description to macroscopic description can be shown from the transport equation, which describes a lot of the physical phenomena we want to talk about. So what it does is describes how particles move around and they can collide with each other, they can be influenced by forces, whatever, but the point being is that in one space you have a distribution of velocities, so particles if we zoom in on a little bit of gas in this room, it will have particles moving at a bunch of different velocities. That also can vary in space, and it can also evolve in time. So the problem becomes 7-dimensional, this transport equation. So that's quite high dimensional, it's quite difficult to solve. Often what we do is we integrate out the velocity dimension, we say we want to average over that, and then just describe how things change in space and time. So hydrodynamics, you take the transport equation and integrate out the velocity dimension. So you've gone from 7 dimensions to 4. But we want to, all these terms here, once we integrate out, form closures that we need to give closure relations for. So let's give an example. So I was speaking about hydrodynamics. We take that transport equation, we integrate out velocity space, we give this equation here, which just describes that, it's called the continuity equation. It says that your number of particles is fixed. So if tons of particles flow in here, they must have left from over here, and this ensures that the total number of particle number doesn't change. You just increase density here, decrease density here. But what appears is a velocity term that we don't have an equation for. This is an equation for the number density, and our velocity has appeared. Okay, so let's multiply the velocity, integrate space out again. We get this equation for how momentum changes, so momentum is conserved. And then another term appears, which is the pressure. Oh, we can do it again. You just keep on going, and you always get that your equation always has a term that's linked by one higher moment. So you kind of get into this situation where you always have to say, okay, I stop. I've got enough moment equations. What does this term actually equal? What does this closure actually equal? And therein lies the problem. So a really commonly used sort of closure relation is this thing called flux-limited diffusion. So I stuck it into Google Scholar. There's quite a few results. It's used in many different fields. And it is a real problem for predictive power of simulation codes, especially in my field. So what we end up with, what flux-limited diffusion looks like, is you have a diffusion equation. So we've got some here for E because of energy density, but for anything where the flux term depends on the gradient in E, and we've got a time derivative in E, so that's a second derivative in space, so it looks a bit like diffusion. But what we do is we stick this lambda value out here, which we call the flux limiter, and if F gets too big, it prevents the flux from getting too big. So this flux limiter is really ad hoc. People pick values for it, pick functional dependence for it, and it's not necessarily physically motivated. It's just the flux has got too big, stop. So if we could learn a better flux limiter, that would really improve how we can solve these equations. So let's link that back to everything we've been talking about with the adjoint state problem and whatever. So what optimization problem is, what is the best closure? So we need three things in order to do that. So we need some data which is a better solution than what we've got. So either it's experimental data or it's a solution to the full transport problem if we can actually pull that off, or it's just slightly higher order than the one we've got, or it's a completely different way of solving it. So say we could track the trajectory of all the particles and not explicitly solve this transport equation, but like sort of look at the trajectory of particles and then build the pressure and the density and the velocity out of that. You might call that a stochastic simulator, but break it down into little particles as opposed to evolving this fluid. That again would represent a higher order solution. So we need something like that. We also need the reduced order model, the thing that's got closures in it, but we need a way of parameterizing the closure so that it's learnable. So you might think, oh, we can do this as a neural network, and that's something I've tried, or maybe just something simpler like a power series or a Pade approximate or something like that. But basically, you need your closure relation to be learnable. So you might want to introduce some physical intuition as to what this parameterization looks like, because a neural network might allow unphysical values for the pressure, for example. So you need a way of also encoding any physics you know in this closure. And then the last thing, which turns out now to be the easiest thing, is a means to update the parameters to find the optimum. So as long as we have written our lower order solution in a differentiable programming manner, then we can get the gradients for free and we can do gradient-based optimization. If we didn't have this, we might consider doing a gradient-free optimization, but then if you have more and more parameters, it gets slower and slower, and then this might become intractable. So I'd say now we have a very obvious number 3. We hopefully have number 1. The real question is how you do this well. So this comes into the importance of inductive bias, which took me ages to find what mathematicians meant by this. And turns out it means like physical constraints, like don't disobey the laws of physics. That's inductive bias. It's really important in this case because obviously these are physical models, so we want them to respect physics, but for other reasons as well. So I think probably the most important one is the fact that we're probably going to have really small data sets because that data we required was maybe from experiment or some higher order solution. They're very expensive, both of them, in time or money or whatever. So we want something that's trainable with small data sets. If you include physical laws, you've got less to learn. So it's always useful, if possible, to include as many as you can. It's also nice if you do that, if you include those physical laws, because it means that you can take your model and apply it to something that wasn't in the training of data at all, and it's probably adaptable. Whereas if you give it free rein, it will probably match your training data really, really well, but will be very poorly adaptable. So it's also important for that. And also it helps you conserve things. So often your physical constraint might be conserve energy or momentum or something. So it helps maintain those. I spoke before with the physics-inspired neural networks. We could put these constraints into the loss and optimize for them. I don't like that as much as encoding the constraint by construction in the closure or in the differential equations. I've seen this called solver in the loop or embedded or trajectory fitting approach to it. So where rather than training your closure separately on data and then it doesn't necessarily obey the differential equation it's part of, you keep the differential equation inside the optimization. So the thing we've been talking about all morning, so that you make sure that the differential equation is being solved when you train the thing. That does do some interesting things though. So in this paper, they describe it a bit better, but because you're doing a numerical solution to a differential equation, it's got errors in. So when you train to match the data as well as possible, you might actually be training your closure to correct all the problems with your numerical solution. So it's both learning physical laws and also how to correct your numerical solution. So that could be seen as an added bonus, but then if you go to interpret it, it might muddy the water a bit because it's got terms in there which are just like, I did this because if I didn't, the numerical solution went unstable. So it was actually just correcting for the numerics as opposed to learning some physics. Okay, so for my example, I'm going to talk about radiation transport. So radiation, by which I mean like photons, and radiation moving through matter obeys a transport equation. It can be absorbed and emitted. Photons move at the speed of light, don't experience forces. So all these things are the physical laws we're going to want to encode. So we want to make sure when it comes to defining our equations that we don't mess up any of these. But what we're going to do is we don't want to solve the path of all the photons moving in any direction. We want to reduce that complexity by integrating out the angular domain. So rather than looking at the number of photons at this point moving in that direction at this time, we just say, what are the number of photons at this point? What are the flux of photons in this direction at that point? So we come up with summary statistics about what the angular domain looks like rather than having it resolved in angle. So we kind of get, in the simplest terms, we get the mean, the variance, and whatever of the angular domain, and we solve for those as opposed for discretizing the angular domain. So hopefully that makes sense. So closure relations are going to appear because those summary statistics don't tell you absolutely everything about the angular domain. So what does it look like? So I've made some little very low effort PowerPoint slides showing the problem we're going to use to train a closure. It's an analytic solution, so in terms of higher order, it is the highest order. It is exactly correct, the exact solution to this particular problem. It's very, very simple, therefore, because you can only do analytic solutions to very simple scenarios, but it's a great test bed because we can see how close we can get. So what it is like we have this like block of absorbing matter that's initially cold, and then in the middle of it, we just suddenly release some photons. And they're going to stream out from that central location. Some of them are going to be absorbed and heat up the matter, and then it's going to start emitting, and you'll get like this wave that moves outwards. So yeah, after a little bit of time, the photons have moved out a bit, there's still some being made in the middle, and it starts to heat up the surrounding region. And then at the furthest extent, they're just moving outward from where they were spawned initially. So we're going to have this sort of layered structure where it's going to be the most number of photons in the middle, and then it sort of decays outwards. And then right at the late time in this test case, this external source of photons turns off and the thing is just allowed to relax. And the reason why this was particularly interesting is because the late time behavior, when it's relaxing, should relax to diffusion. So because we want to train flux-limited diffusion, ensuring that we get the late time behavior correct is ensuring that the thing we solve still actually gets diffusion correct, and we don't get rid of the useful bit of flux-limited diffusion. But at the earlier times, when the angular domain is more anisotropic, that is, our summary statistics do a poor job of representing the angular domain, we can do a better job. So this late time behavior is diffusion, so flux-limited diffusion would get that right. So that it's the early and middling times where the diffusion model doesn't do so well. So let's go back to our abstraction just to hopefully cement what's going on. We have our reduced model for radiation transport with some parameters. The loss term is making sure that we compare to the Sue-Olson test problem, which is this thing here, and make sure that the energy density of photons, so the number of photons at a given time, at a given space, is as close to the Sue-Olson problem as possible. And then at the same time, we use discretize and optimize to get the gradients of our parameters that define our closure. So very similar to our very simple ODE example, but it's a PDE. So here are the results. So what we have here is the black points are the training data. This is a function of x, and then this is at early time, and as it goes up, that's going towards later time. So it's all the different time plots plotted on the same plot. So sorry if that's a bit confusing. And the best literature closure is this Larson 2 flux-emitted diffusion. And you can see it does okay towards the beginning, but towards the later times when it's at the peak of this emission in the middle, it really dips and doesn't do a very good job of describing it. And this is what's used in most radiation hydrodynamics codes, that's hard to say, is this Larson 2 flux-emitted diffusion. So, it can't do this simple test problem, so that's quite concerning. So can we do better? Can we train a better flux limiter? So we've got two different models here. One which modifies the flux limiter, but using a form of the flux limiter that's from the literature, from old literature, so not with trainable parameters. It just takes the same functional structure, but just replaces the fixed terms with trainable parameters, and that does a bit better. And then this one here is where we don't use anything from the literature to constrain what the flux limiter should look like. We just allow a generic function approximator called H to describe the flux limiter, and we train that, and that does really well. So we can see we can improve on this and get a way better model for flux-limited diffusion. And once this training is done, and we have this, we can just transpose it back into our model. It's not, there is no, in this case, there's no neural network involved, it's just a parameterized closure. So you could just adopt this model with exactly the same difficulty as it is to adopt the Larson 2. So it's just an improvement on this. You might ask how well does these generalize? We've trained it on this data. In this work, we also looked at including other sources in other locations, and it generalizes just as well as the Larson 2. And that's because we've included it in part of this equation and included those physical constraints as inductive bias. So it is an adaptable closure. So yeah, the conclusion of the work was we can improve on the closures. So in here is like the loss with respect to the Sue-Olson test data. In black are a bunch of different ones from the literature. You can see, they don't do so well. And then in red are a bunch of different models. I showed this one here, which are the flux-limited diffusion equations that we relearned, and they do way, way better on that. And this is a very, very, it was a very, very simple closure. So you can imagine scaling this up to a more complicated problem than source and still improve over what we've been using for a long time, this Larsen 2 flux-limited diffusion. And this is just one transport problem. There's so many transport problems. I might go back a very long way and get to the laundry list of transport that's in Chimera. But should have copied the slide. And then we'll have to go back the other way. I regret this decision. Right. There's radiation transport. That, again, we're learning closures that improve our accuracy in the angular domain. Alpha particle transport. So in the fusion reaction, alpha particles are made and they're so much hotter than the background plasma that they sort of stream out for long distances. So they can't be described by hydrodynamics. So instead, we have to have another transport model. This, again, is very computationally expensive to solve for, so having a reduced order model for that would be good. Thermal conduction, again, is flux-limited diffusion. The flux limiter in thermal conduction has been the subject of argument for a very, very long time. You get to ridiculous situations where people, in a conference stick their hand up and their question is, what value of the flux limiter did you use? Was it 0.06 or 0.15? I don't believe you for whatever value it is, right? So if we can train a flux limiter that actually represents what's going on in the higher order solution and improve on that, that would improve our predictive capability. So these closure relations are absolutely littered through this laundry list of physics problems. And as long as we can find a scenario where we can train these sort of offline and include them back in, it will be a boon to this numerical modeling. Right, I'm sorry, let's go back all the way through. Cool. So yeah, I just thought I'd leave right at the end with a summary of the topics and some good references for those. It's quite a big topic, and I've probably, as a newbie in it, focused on bits that are particularly relevant to me in terms of they're very much related to physics and PDEs. I'm sure if you dive into this, there is a lot more to be found because it is a very broad topic. But yeah, no, with that, I'll answer any questions. Have you got any? I realise how long have I got? 15 minutes. Yeah?
I've got a question. Like you mentioned that how they generalize. So once you train it on a set of parameters for this equation,
Yeah.
And you were to use it like for a different set of parameters. So like something where it doesn't have any information about those black points.
Yeah.
And you said that it works as well as the Larsen.
Yeah.
That's quite interesting. Is that is it mainly expected because of how you limited the training and you managed to get the neural network to actually obey these laws that?
Yeah, so the important bit was, so lambda is the flux limiter, and then it is a function of it's actually just a function of, in this case, just one scalar parameter. And we know a bunch of different constraints about it. So we know the value has to be 0 here, and the gradient has to be 1. At 1/3, it needs to equal 1/3. And then at this end, it needs a certain gradient as well. If you don't enforce these 3, it does a terrible job at generalizing, but it goes through absolutely every single point. But by doing these, it like sort of picks up a certain form that generalizes well. So I think, because it's quite a simple like scalar function, and you've given it 4 points or gradients it needs to go through, it generalizes quite well. I think that's more a testimony to the physical constraints being included than the generalizability of the machine learning part of the free parameters of the model. I think it would generalize. It will be more difficult in a problem where you don't have these well-known points. If you just knew it went through 0 here and nothing else, it probably wouldn't generalize as well. You're restricting its freedom to find a truly bonkers solution that goes through.
Like you had like an example of Navia's talk, like where they looked at the error. If you had like an error on the viscosity, and it can get that back.
It's not an error on the viscosity. It's they add noise to the training data.
Okay, and then it kind of gets back.
Yeah. So it's
Right.
still pretty close. It's within 5% of the true value when you add noise. So that's a useful test because either your data could come from a stochastic simulator, in which case it would have noise, numerical noise, or it could be experimental data. So 1% noise is quite a low amount of noise. So you introduce 5% here, maybe more realistically, you're in the 5 to 10%, and the error grows a bit on that inferred viscosity. I wonder if you could have like a variational neural network keep track of a range of values of viscosity that works rather than just finding a best fit. But yeah, it's useful to see it's at least a little bit robust to the presence of noise, because that's a common scenario.
Like if they were to have different, like if they were to train their neural network on a certain set of viscosities and then try and predict something with a different set of viscosities, that would just work.
It did not work, no. Yeah, this is the viscosity that matches the training data. So yeah, I think there would be an example in the radiation transport. I've said here, it does well on a modified problem where I introduced an additional source at a different X location. But it was in if you introduce something that wasn't in the training data at all, like rather than just matter absorbing radiation, it also scatters it. It would lose its predictive power, I think.
You would need to actually train it on all the data or all the scenarios that you think are relevant.
Yeah.
Then it can generalize from there on.
Yeah, it can generalize within limits. I think with these things, at least where I'm thinking of going, say for the alpha particle transport, is having basically allowing it to be an interpolator. So only have the training data encompass all the reasonable scenarios I expect to see. And then you have a lot more trust in it. Like, it's not guaranteed to generalize. This was lucky enough that in this simple transport problem, it did generalize, and we had good physical constraints. But I don't think it's a guarantee of these types of models. So I think the best case is training data encompasses all the regions you expect to find the model, all the parameter regions.
Aidan,